Hello. Hello, everybody. It is my great pleasure to introduce our speaker today, Dr. Naoki Kubota. Dr. Kubota, he is an associate professor at the College of Science and Technology at Nihon University, Japan. His
Yeah,
research lies in the field of probability theory with particular focus on random walks in random environment, per-stage percolation, and the Forg model. Through his work, he has shed new light on complex phenomena in stochastic processes, offering both deep theoretical insights and innovative methods. In his remarkable paper, Gaussian fluctuations for superdiffusive elephant random walks, Dr. Kibuta was the first to successfully study the fluctuations of the elephant random walk around its limiting behavior in the superdiffusive region. Personally, I've had a lot of pleasure reading his work. His papers are not only clearly written and mathematically rich, but also full of elegant techniques and inspiring results. Thank you so much, Dr. Kibuta, for your generosity in accepting to speak at this webinar. The floor is yours. Please go ahead.
yeah. Thank you for the introduction. I'm very happy to be invited to this very nice seminar. So when I get the email from Rafik for the first, so I was very surprised. So that so I didn't understand why I was invited to this seminar. So because I don't have any connection to the KSA. I'm very happy to contract the connection to the KSA or researchers. Okay, so first I didn't understand why my information how my information is spread to the KSA. So that information spreading is very mysterious and very interesting for the research. So today's topic is very related to the information spreading. So in particular, so recently I have been studying the first passive calculation and its related models. In particular, so today I want to treat the so-called frog model. So which is one of the model to describe the information spreading. Okay, so in particular, today's topic is in the so-called frog model. So I want to explain the behavior of propagation in the frog model, and introduce the result. So I have studied in this field. Okay. So first of all, I want to explain the frog model. Okay. So in this talk, we consider the frog model and its underlying space is the d-dimensional lattice ZD, and D is equal to and so bigger than 2 in this way. Okay, so roughly speaking, that frog model is one of interacting particle system, so consisting of two states. So one is sweeping and active. Okay, so please see the picture. So that the underlying space is ZD, and D is bigger than or equal to 2. So in this picture, so we put sleeping frog in this way. So on each side of ZD, according to Bernoulli distribution. Of course, generally, so we can consider the frog model. So for the general distribution to put the sleeping frog on ZD, but so in this picture we now consider the Bernoulli distribution. That is, each side has at most one sleeping frog in this way. Okay, and in particular, we put active frog. Active frog means that so this frog wakes up and move, and so can move randomly. Okay, so other frogs sitting on side are sleeping now. So first, so this original active frog performs simple random walks, simple random walk in this way, and so move around ZD randomly. Uh, at this point, this sleeping frog is hit by this active frog. Then the sleeping frog wakes up and becomes active in this way. We now have two active frogs. Okay, so these two active frogs perform simple random walk independently and move over ZD randomly in this way. So, and this active frog go to this direction, for example, and this active frog meet this sleeping frog at some point. Then this active frog, this sleeping frog wakes up and become active. Okay, at this stage, so we have three active frogs.
Uh,
And
sorry,
these three active frogs,
sorry, question.
okay?
When a frog is active, it will be active for the rest of all the time when a frog is
Uh,
active.
uh-huh.
It is active
So,
for all the future, or can
yeah.
be.
Yeah. So once the sleeping frog become active, so that frog is active forever
Okay,
and
okay,
perform simple random walk.
okay. Thank you.
Yep. So repeating the procedure to for the remaining sleeping frogs and for the coming active frog in this way. Okay, so all active frogs perform simple random walks independently. Okay. And so this are active and become active and perform simple random walks independently in this way. Okay, so roughly speaking, this is a rough exploration of the frog model, and then so we can observe. We want to observe the propagation of active frogs. Okay, so this model is originally introduced. So originally, so it comes from an information spreading. So this model is originally so introduced by Ravi Shankar around so 19 and around 2000. Okay, so I like animals, so I prefer using the name of this model is the frog model, but this frog model has already many so names depending on the situation. So in particular, so usually, so we can see the following two names, so combustion model and reaction model. So A plus B to 2A. Okay. So these names are often used in the situation the continuous time simple random walk. Okay, sorry. So today's talk, so we consider the simple random walk as the discrete time simple random walk. Okay, but of course we can consider the continuous time model, and so when we consider the continuous time model, we so these two names are often used. Okay, and so the frog model is originally comes from the information spreading, but so this model is regarded as combustion or chemical phenomena. Uh, okay, so this is a history of the frog model. Okay, so. At the beginning, so frog model, the recurrence and transience problem are studied in the frog model. Okay, so recurrent means that the origin is visited by the active frog infinitely or many with probability 1. And transient is not recurrent. Okay, so at the beginning, so this recurrent and transient problem has been studied. But so I'm interested in the spreading of information, which is original motivation to consider a frog model. So I'm interested in the speed of spread of active frogs. So how first do active frogs spread across the ZD?
Just a general question. The number of
Okay.
frogs is finite or infinite or
Yeah, both case okay.
okay.
Yeah, but so usually so we put finitely many sleeping frog on the size of ZD. So if we consider the case where the we put sleeping frog infinitely many, uh, this case is very so easy because we can use our infinitely many frogs. From the beginning, so that expression spread is very simple. Uh,
Okay.
Usually, we put on a finite sleeping frog on each side. Okay. Yeah. The, today's topic is the speed of the spread of active frogs. Okay. So to explain the result of the frog model precisely, so let me introduce the following notation. Okay, so omega x is a number of frogs sitting on the site x. Okay, and this family so describes the initial configuration of sleeping frogs on ZD. Okay, and so S SKXL is the trajectory of active frog starting at the site X. And L is the so, number of frogs sitting on the site X. Okay, so this is a family of independent simple random walks.
And L,
Okay,
what means L? Yes.
R is the number of well, for example, so is equal to one. This means that the first flock sitting on the side X. Okay, so if L equal two, that means that is the second flock sitting on the side X.
That means that we have two frogs in the site X.
Yeah.
Okay.
Yeah, so in this model, so we can put many flocks on the same site. So L is also number of the flock. Okay, so in index of the flock. Okay, so and then we consider the underlying. So this product probability measure as the underlying probability measure of the flock model. So this means that the initial configuration and the behavior of the active flock are independent. Okay, so this is a basic notation in this talk. Yep. Okay, so I'm interested in the spread of active flock over time, and the, to analyze the speed of spread of active flock. So we consider the first passage time. So first passage time txy means that. So uh, if we s- if we put active frog on the side x, of course. So after that, so many active frogs will be generated by original active frog and by the coming active frog. Then, this time is the first time when an active frog reaches a site X. The former is this time is defined by this. Yep, this is the minimum time when the propagation of active frogs starting at X reaches Y. Okay, so usually, tau xi plus 1 is a hitting time of the simple random walk starting at side xi to a side xi plus 1. Please look at this picture. So this is the one example to achieve the first passage time from x to y. When we put the active frog the, on this side X, so this original site generate and original active frog generate the, the active frog. So in this environment, to achieve the first passage time, so this original active frog is switched here and this active frog and continue the same procedure, and we can get the path of frogs to achieve the first passage time in this way. Okay, tau xi plus 1 is a time for one active frog to achieve the first passing time. Okay, so this is the time or the minimum time when the propagation of active frog starting at side X reaches Y. And if we can study, analyze the behavior of this first passage time, we can to observe the behavior of the propagation of active frog. So more precisely, so by using first passage time, so the propagation of active frogs is described as follows. So BT is a set of all side Y, uh, which whose the first passage time is smaller than or equal to T. Okay, so BT is a set of all sites visited by active frogs within time T. Okay, so the following natural question arises. So how does a random set behave as t to infinity for a fixed law of the initial configuration omega? And the second question is this propagation of active frog depend on the law of the initial configuration omega. Okay. So these two questions are very natural when we consider the behavior of the propagation of active frogs. Okay, so to answer this question, we first consider the behavior of the first passage time. The following is the essential property of the first passage time. The first passage time satisfies the triangle inequality. Okay, and we are now working on the IID setting. So the initial configuration is, okay, sorry, so initial configuration omega is independent random variables taking values in N0. And the S is a independent, the family of independent simple random walks on ZD. So we are now working on IID setting. So the first passage time, the family of first passage time is stationary ergodic with respect to the shift for each direction. Okay, so so this kind of quantity has been studied in the first passage calculation. Okay, but usually first passage calculation, only one randomness. But in the frog model, we have two randomness. So random initial configuration and simple random walks. Okay, so to analyze the behavior of the propagation of active frogs, we have to control the initial configuration omega and the behavior of the simple random walk at the same time. So in addition, so our first passage time is regarded as a long-range version of the first passage calculation. So this is because so tau xi to xi plus 1. So this is a hitting time the simple random walk. But so xi and xi plus 1 may not be nearest neighbors. Okay. So these are the difficulty of the frog model compared with the related model of Okay, so by using this essential properties, so Arbest or et al. So prove the following asymptotic behavior of the first passage time. So first passage, there exists non-random norm mu on RD such that for x, the first passage time from zero, the origin to the site nx divided by n converges to this norm mu x almost surely and in L1. Okay. So roughly speaking, so this says that we can, so the first passage time is controlled by the non-random quantity mu in this way. So the first passage time is random quantity, but so, okay, so sorry. So mu x is non-random quantity, but so they are comparable in this way. So, to analyze the propagation of active frogs, it is sufficient to study the behavior of this non-random quantity mu. Okay, so this norm mu is called the time constant. Okay, but to get this asymptotic behavior, the following is an important point to get this asymptotic behavior. Mainly, so Arbes et al. So proves that this integrability for the first passage time. Okay, so the other essential property of the first passage time and this integrability, so we can use the subadditive ergodic theorem to observe the asymptotic behavior of the first passage time in this way. So mainly, so to get this integrability, so we have to control the frog active behavior of active frog and the initial configuration roughly. Rough estimate are needed to get this integrability. Okay, so it is not. I think it is not this difficult, but so we have to control the initial configuration and the simple random walk at the same time to get this result. Okay. Yeah, of course. So we can get asymptotic behavior of the first passage time. Similarly, so we can get the behavior of the set visited by the active frog within time t in this way. Okay. So this kind of result is called the shape theorem. This is the shape theorem in the frog model. So BT is a site visited by an active frog within time t. This random set BT is controlled by a non-random set B in this way. Okay. Roughly speaking, this random region is comparable by using TB in this way. So the subadditive ergodic theorem only gives the existence of the time constant. plus trivial properties. But we don't have any more detailed information on the for the time constant. Okay, so to study the propagation of active frogs more precisely, we have to analyze the time constant more precisely. So beyond the subadditive ergodic theorem. Okay. And the following the question of about the time constant. Okay, to analyze the behavior of propagation of active frogs, we have to study the time constant more precisely. Okay, so to simplify the notation, the statement, so from now on, so we focus on the Bernoulli setting. So this means that we put sweeping frog on each side of ZD according to the Bernoulli distribution of parameter R in this way. And so mu Rx is a time constant correspond to the parameter R of the Bernoulli distribution. Okay, so then the following is a question, is a natural question. So is the time constant mu Rx is continuous in the parameter R? And the second is, so the time constant mu Rx is strictly increasing in R. Okay, so it is clear that this time constant is non-increasing in R. So because the R is a probability that we put sleeping frog on each side. So if as R to 0, the number of frogs we can use decrease. So the time constant is non-increasing. Non-increase. Sorry, yeah, yeah. Non, okay. So maybe this is typo decreasing. Sorry. Okay, so the third question is how large is the difference? Uh, how large is the difference mu p r x these time constant? This is their natural question for the time constant depending on the initial config the law of initial configuration. Okay, so in the remaining, so we explain the result. So results that I obtained for these questions. Okay, so the first is continuity. Okay, now so we consider the Bernoulli setting. So this means that so we put one sleeping frog on each side with probability R. And so each side of ZD has no frog with probability 1 minus R. Then, so in this case, so we can get the continuity for the time constant in parameter R in this way. for any R0 is fixed, and then so time constant of parameter R is converges to time constant of parameter R0 as R to R0 in this way. Okay. Yeah. Of course, we can generalize this result to more general law of the initial configuration in this way. Okay, so phi n is converges weakly to law of phi, and the phi n the expectation of the initial configuration for the law of initial configuration are uniformly bounded. Then we can get the same result in the more general setting. Okay, so in the Bernoulli setting, so these two assumptions are satisfied, and we can, this is a corollary of this general result. Okay, so rough idea of the proof of the continuity of time constant is the following. Okay, so we write omega r is for the initial configuration for the parameter r in the Bernoulli setting. Okay, so roughly speaking, so r is very close to r0. The initial configuration omega r of the parameter r is approximately equal to the initial configuration of parameter r0 in this way. Okay. To derive this fact, so we have to control the initial configuration precisely by using a population argument. So in particular, so coupling argument and by using the cluster of the population and so on. So, but anyway, so we have to study the initial configuration more precisely, so by using a population argument. Okay, so yeah, of course, so the configuration, initial configuration, and they are very close. Then the first pass, those first passage time are also very close. So the first passage time, if R is very close to R0, the first passage time in the initial configuration omega R is approximately equal to the first passage time in the initial configuration omega R0, and they are divided by n, and they converge time constant mu r, and this converges to time constant mu r x mu r 0. Okay, so this means that so mu rx converges to the time constant mu r0 as r to r0. Okay, so this is a very rough picture. This converges. So let arrows describe the parts achieving the fast passage time in the initial configuration omega r0. Of course, so omega r is the number of flocks is fewer than number of flocks in the initial configuration omega r0, but omega r0 is cross when R is very close to R0, then we can use the number of frogs we can use to achieve the fast passage time is getting larger and larger. So if R converges to R0 from below, then finally, so we can use the same initial configuration to achieve the first passage time. Okay, and after we can get this converges the continuity of the time constant in parameter R. Okay, so this is a rough idea of the continuity of the time constant in parameter R. Okay. Okay, let's go to the second and third questions. Okay, so second question is a strict monotonicity. So, and the third is a difference between time constant in parameter R. Okay, so we can get the following result. And so first we fix R0. Okay, so there exists constant C and C prime. They are depend on the dimension of the lattice D and the fixed parameter R there. Okay, such that so if we consider the two parameters P and Q in this way, then we can get this difference, this estimate for the difference between the in the time constant mu p and mu q in this way. Okay, roughly speaking, so this difference is controlled by the quantity, so q minus p. So q minus p is also difference between the Bernoulli the parameters of the Bernoulli distribution. Okay, so this result was obtained by joint work of Baron Hao-Kan and Shuta Nakajima. Okay, so as a corollary of this result, we can get the locally explicit continuity for the time constant mu r. Okay, so not a complete implicit continuity. So because we first fix parameter r0, and if so mu r is Lipschitz continuous on this interval. Okay, so this means that so locally Lipschitz continuous. The time constant satisfies the locally Lipschitz continuity. So in addition, so this parameter R0 is fixed arbitrarily. So we can R0 goes to 0. So we cannot get so complete Lipschitz continuity, but we can observe the strict monotonicity for the parameter R in this way. So if P is strictly smaller than Q, then the time constant mu P is strictly bigger than mu Q in this way. Yeah, this means that so the time constant mu Rx is strictly decreasing in R uh, in this arm. Okay, so unfortunately, this result, I think it is difficult to extend this result to more general, the law of initial configuration. So this is because that proof, reason comes from the proof of the this Lipschitz type estimate. Okay, so to get this result, we estimate the following so derivative of the expectation of the first passage time. Okay, roughly speaking, if we get this estimate by integrating so both side over this interval, then so we get this difference between the first pass the expectation of the first passage times, and both side divided by n, and taking y is equal to nx, and then so as n to infinity, the right side converges to the difference between two time constant, and so this is approximately bounded from below and above this quantity. And desired estimate, we get the desired estimate for the difference between the time constant. Okay, to estimate this derivative, so I use Russo's formula, which is a very famous the formula in the percolation model. Okay, to apply the Russo's formula to our setting, so it is needed to consider the Bernoulli initial configuration. Okay, so that this result, I think so. This result is a little bit difficult to extend to more general setting. Okay, okay. So last about 2 or 3 minutes. Okay, so finally, so we give the rough rough idea proof of the this result. Okay, so okay, it is sufficient to estimate this, get this estimate. And to estimate this derivative, so we use Russo's formula for this random variable. The roughly speaking, Russo's formula gives the how large the effect of the first passage time when we change only the state when we change the state of only one site. Okay, so roughly speaking, so this derivative is equal to is described by using this summation, so by using the Russo's formula. This difference is equal to 0 if these two fast passage time do not use the site, do not use the frog sitting on the site Z. So because this is only one state is changed on the site Z. So we can put this restriction in the expectation. But so this difference is not so large. This is because we can find it so allowable by pairs around the site Z. So even if we don't use the site Z, we can find by pairs with not so large the time to from here and here. Okay. So this difference is not too large, and we can roughly speaking, we can get this. Uh, we can estimate this difference by using some constant, and so this expectation is bounded from above and below the expectation of this summation. Okay, so this sum means that the sites in the okay, sorry, so R0x and R0y means that the path of active flux attaining the this fast passage time. Okay, so finally, so this the derivative is bounded from below and above by using the number of flux containing in this path attaining the fast passage time. Okay. And roughly speaking, so this number of active frog containing in this path is bounded from below and above by the L1 norm of the target point Y. And we can get the desired bound for the derivative of the expectation of the first passage time. And there get the Lipschitz type estimate for the first passage time for the time constant. Okay, it's over time graphic.
Yes, yes, please.
Okay, yes, thank you. Thank you for hearing my presentation. That's all.
Thank you, Dr. Kubota, for this talk. Are there some questions, please? So Txy is the number of times to go from X to Y. Okay?
The
first question, not question, but just a remark, is Txy equals in distribution to T0 Y minus X. Txy equals in distribution to T0 Y minus X.
Oh, yeah. So the same distribution.
Okay.
For this, and
you said
X,
for this you said only T0X. Okay. The Xi here, the points of the trajectory to go to X to Y are random. Sure.
Random. So Xi are random. So
and what represents Xi plus 1 to Xi is the second point after visited by Xi. Is that true?
Yeah.
Okay. Okay.
So in this setting, so to take infimum in the definition, we consider all the sequence on ZD, but so this so roughly think this is a hitting time for the simple random walk, but so we have to assume that if xi has no sweeping flock,
Okay.
then this is always equal to infinity.
Okay. Okay. So the active frog can go to a position where there are sleeping frog.
Yeah, yeah, yeah,
Not it cannot go to a free position.
yeah, yeah, yeah.
Okay. Okay. Uh, uh, and have you some maybe you have presented this result, but have you some results about the asymptotic behavior of txy, where
Yeah, yeah.
where y goes to where the distance between x and y goes to infinity? Are there some
Mhm.
results about the asymptotic behavior about the behavior in distribution of t0x? Okay, where x goes to infinity.
Yeah.
There are some results here. You have some results.
Um, so x and y to both go to infinity, right?
Okay, but the distance between x and y goes to infinity. The norm
Mm.
of y minus x goes to infinity.
Okay. Mm, yeah, I don't see that the exact paper discussing that situation, but it we can get the similar result of in that case.
Okay.
Yeah, yeah.
Other
So
other question from the second kind. Are there
mm,
some results about the cardinal of BT, the number
mhm,
of uh, points visited up to time t?
mhm.
Are there some results about the norm of BT?
Uh-huh. No. So do you ask me about the result for the cardinality of
Yes, B
BT,
of
right?
T. Yes, yes.
Yeah, rough thing. So B of T is behave like non-random set B. So rough things are BT, the cardinality of BT is grows linearly in
In
time
T. Yeah,
t,
okay, in time T. Okay.
yeah,
So
t
it goes to
to
plus infinity.
yeah, 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 yeah,
But BT over T, for example,
yeah, yeah, yeah,
have some behavior or not? BT
yeah,
divided by T
yeah, yeah, yeah,
can goes to some
yeah, 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 yeah,
some limit. Okay,
yeah.
another question that I think it will be interesting. What about the first return to zero? If the frog starts
Mm,
from the point zero, from the origin,
mm,
what about the time to return for the first time to zero?
mm. So time to
The recurrence
zero.
and the transience of this.
Ha, 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 ha. So, yeah, maybe so uh, in this case, uh, uh, so, but, uh, so do you ask me about the transients and recurrence
Yes.
problem?
Mhm.
In this setting?
Yes. Yes.
Maybe so. So I didn't remember very well, but so the transition and the recurrence problem has been studied by so many people, and so in this case, the frog model is recurrent. So even if we consider the dimension is bigger than 3. If the initial configuration, the row of initial configuration, depending on the row of initial configuration.
Okay, okay,
So yeah, because we can in the frog models with random initial configuration, so we can use we may use a lot of sleeping frog.
okay, okay. Another question, and the last question. If we
Okay.
suppose any active frog can sleep for an exponential time of parameter
Okay.
1, for example, and after he can move,
Uh-huh.
we can obtain some results using yours here.
Yeah, so that that model is known by the activated random walk.
Mhm,
So, and that case is a little bit difficult than the original fork model because we may not use the sub additivity for the first passage time. So, okay, for
okay,
example, so in that case, this triangle inequality may not be satisfied. So it is more difficult
I think
to,
that the triangular inequality is satisfied, no?
yeah, yeah, yeah,
For,
yeah.
for
So
this model.
yeah, 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 yeah. So if we can, we consider that the active frog can sleep at some point,
Mhm.
then the triangle inequality may not hold. So in that case, so it is difficult to observe the asymptotic behavior of the first passage time. But similar, i- if we can go find the same similar structure of that model, we can the same procedure may work to observe the asymptotic behavior of the first passing time.
Okay, okay. The last question, I'm sure the last question. If we go to the theorem of Kubota 2024, please.
Okay.
Theorem Kubota 2024. Okay, okay. And you take x equals 0 here in this theorem.
Mm-hmm.
X equals 0. So we deduce that mu p0 equals to mu q0 for all q and q,
Mm-hmm.
for all p and q.
Yeah, yeah, yeah. So the first time constant of 0 is always equal to 0.
Okay, okay.
Yeah, yeah,
Mhm.
because so roughly speaking, so this uh, x equals 0. So okay, so the time constant is the so the convergence this convergence to time constant mu x. But if x equals 0,
Yes,
or this equals 0, the time
yes,
constant
yes.
from 0 to
Sure.
0 is equals 0. Okay, so this case is if x is equal to 0, this
Mhm.
is always equal to 0.
Okay, thank you. Thank you. Are there other questions, please?
Yes, please, I have a question.
Yes, Dr. Abdulsattar, please.
Thank you very much, Dr.
Thank
Kubota,
you.
for this nice talk. Indeed, I have a question concerning the
Okay,
definition of TXY. If
okay.
you can
Definition
provide
of
with that.
dxy. Okay, okay.
Okay, this one. Is it possible to restrict this expression for the case where ixa plus 1 are nearest neighbors?
So sorry, oh, I cannot
Is it
hear.
possible like to just take the case where xi plus 1 are nearest neighbors here?
Ha, 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 ha. Sorry, xy plus 1 stay here. Hmm.
But the frog can make a step of size more than one.
But here is dealing
yeah,
with
more than, yeah.
simple random works. But you are within the simple random works framework. So if you take tau of xi plus 1 is the first time where the random work starting in xi reaching xi plus 1. Therefore, it will reach one of the nearest neighbor before reaching xi plus 1. Yes? Because it's a simple random work. The steps are 1. Yes?
Mm-hmm.
Therefore, before you go to xi plus 1, you will pass by, you'll have a passage by a nearest neighbor of xi.
Mm-hmm.
And here, as you can see, the infimum is considered over all the possible configurations. And I think it's the same. If you restrict yourself to the case where xi plus 1 are nearest neighbors, since we are working only with simple random walks.
Mm-hmm. Okay. So, mm, mm, yeah. Yeah, but so okay, so do you ask me that so that okay, so uh there ta
The question that starting, for example, from the point 1, 1, we cannot go directly to the point 3, 3. We can go to the point 1, 2, 2, 1, okay? Just 1, 2, 2, 1, or 0, 1, or 1, 0. Because it is a simple
okay,
random walk.
okay. Yeah. So usually so okay, so do you ask me that so we can use the same point to con so this sequence may contain the same point in the
No, my
sequence.
question is just to take nearest neighbors. X0 is nearest neighbors x1 till xn. I think within the simple random walk framework, it's possible. Because if you can see tau of xi plus 1 is the infimum of time to reach xi plus 1 starting from xi. So before reaching xi plus 1, you will have a passage by a nearest neighbor of xi. And then that time will be less than the time to reach xi plus 1. And then in the infimum here, it's enough to consider the sequence of nearest neighbors since we are in the, see.
Yeah. So yeah, of course, in this definition, so we consider the case where, for example, so this the xi and for example, so this uh, random walk, so from so okay, so from here. And so using this work and so using another side. Of course, so in this definition, we can use the same frogs so many times, but uh, we now take infimum of this summation, this sum. So we remove the in those cases.
Yes, indeed, it's not about taking the same approach, but just taking xi plus 1 nearest neighbors, and it's enough to take the infimum. But second
So
question was, sorry.
yeah, and this it's okay. We so define that this is equal to infinity. So if starting point has no flux. So we define sorry, so I drop this assumption from here. So we decide this time is equal to infinity if the starting point xi has no flux.
Okay, okay. I see it's like somehow a very complicated model of infimum of infinite independent random walk, simple random walks. For the non-simple random walk cases, are there some like
Yeah. Yeah. Usually, this model is when we consider the frog model. So we use simple discrete time simple random walk or continuous time simple random walk. But some people studied the continuum version of the frog model. So the underlying space is RD, and the simple random walk is replaced by the Brownian motion.
I see. I
Yeah,
see.
in that case, has already been studied. But as for example, other cases is that the frog model on so some graph. So instead of RD.
Yeah, yeah, I see. It may be maybe some trees, some tree models. But another question concerning the possibility of having the independent case of the random walks here. For example, you may say the frog at site xi will be stimulated once the first frog visited that site, so that the dynamics become maybe more complicated. Are there some works for the non-independent case?
Yeah, that case can be considered, and it is very interesting. Yeah, but I don't know. So that kind of study in the frog model, but that changes are very nice, I think.
Okay, thank you very much. Thank you.
Yeah, thank you.
Thank you, Dr. Alstar. Are there other questions? Other questions, please? Okay. Sorry. Yes. Other questions? Okay. We have to thank again Dr. Kubota for this nice talk. And before closing this session, I would like to precise that this webinar is an international webinar and not only case A webinar. It is open to all the people around the world. And I would like also to take a moment to remind you that this is the final webinar of this academic year. On behalf of my dear friends and colleagues from the organizing committee, Azhar Ammali, Nabil Gmati, and Wissam Jididi, I would like to express our heartfelt thanks to all of you for your presence throughout the session, for your support, and for your continued interest. We are also deeply grateful to the 21 speakers who kindly accepted our invitations this academic year and shared their work with us. We hope you found the talks insightful and enriching. Please don't hesitate to share with us any feedback or suggestions. They are always welcome and help us improve. Part of next season program is already prepared, and we are happy to announce that the first talk will take place on September 9th at the same time and on the same platform. We wish you all a wonderful summer break, and we look forward to seeing you again soon. Take care. Thank you.
Thank you.
Thank you.